Hello guys, in this video we're going to be looking at quantum computing as you have never heard it before. So what do I mean by this? Well, if you've heard about quantum computing, you've probably heard about things like qubits being in multiple places at once. You've probably heard about wave functions that collapse when you look at them. You probably heard, a lot of weird things like that. Well, in this video we're going to look at quantum computing, but without any of that. There's not going to be any wave functions. We're not going to talk about anything collapsing. We're not going to talk about anything in multiple places at once. We're not even going to use imaginary numbers. I'm also going to include a JavaScript library in the description that's very simple, yet can reproduce universal quantum computing with all the principles I'm going to show in this video. So for some people, this might give you a more intuitive picture of what's going on. So first let's talk about observables. An observable is a physical property of the system that you can measure and assign a value. Think of a qubit like a sphere. A sphere has three axes, x, y, and z. You can perform a measurement on any of these three axes, and hence qubits have three observables, x, y, and z. The measured values are always either +1 or -1, and nothing else. You can't measure z to be 0.2 or something like that. It's only going to be +1 or -1. We can relate a qubit to a traditional bit by saying that it is 0 when z equals +1, and that it is 1 when z equals -1. So now I'm going to introduce this idea called complementarity, which might seem strange, but later on we'll explain it and it will make a bit more sense. But for now, we're just going to assume it. So when you measure a qubit on one axis, it perturbs its observables on the orthogonal axes, also called the complementary observables. For example, you measure a qubit's x-axis and find that it's equal to +1. By measuring the x-axis, you have perturbed the y and z axis, so you don't know those values anymore. This makes it impossible to know all of the values of the qubit at the same time, because gaining information about one interferes with information about the other. This is known as the principle of complementarity. Like I said, later on we'll derive this principle, but for now, just assume it. So now I'm going to introduce something called the expected vector. Don't be scared by the word vector. In mathematics, a vector is just a list of numbers. You can think of it as the same thing as an array. If we can't know all information about a qubit at once, we can represent the qubit using this expected vector. I'm just going to call it E, and the first value is 1, and then the next are x, y, and z. This 1 at the beginning is just used to make the math easier. It's a constant. The first element of the vector is just always 1. It just makes things easier. The expected vector contains a list of numbers called the expectation values, or sometimes called the expected values. These values capture our certainty as to the value of a qubit's observable. An expected value is just a weighted probability. For example, if the probability of the qubit having a particular value of +1 for a given observable is 50% and -1 is 50%, then the expected value is going to be 50% times +1 plus 50% times -1, so it's going to be 0. So an expected value of 0 means it has an equal chance of being +1 or -1. If the probability of the qubit having a particular value of +1 for a given observable is 100% and -1 is 0%, then the expected value is going to be +1. If the probability is 100% it's -1, then the expected value is going to be -1. So I hope that makes sense of expected values. They're just a weighted probability where you weight the +1 or -1 by their probability of actually occurring. Now let's talk about how expectations relate to complementarity. If we know that the particular value of the x observable to be k is going to be +1 or -1, and we know this with maximal certainty, so we're absolutely certain of the value of x, then we must have maximal uncertainty for the values of y and z. So our expected vector will look like 1, k, 0, 0, meaning that the expected value for x is going to be either +1 or -1, and then the expected values for y and z is going to be 0, because we don't know what they are. If we have maximal certainty on y, then we must have maximal uncertainty for x and z. That would give us an expected vector of 1, 0, k, 0. And then if we have maximal certainty on z, then we have maximal uncertainty for x and y. So that would give us an expected vector of 1, 0, 0, k. So now let's talk about the evolution of expectations. So knowledge itself can evolve as the system undergoes physical interactions. This might seem a bit strange, but let me give you a very intuitive understanding of what this means. So imagine, for example, that you know z equals +1. Now you can see this is what our expected vector would look like. You got 1, 0, 0, +1. The first element's always 1, and the last element represents the expected value for z. Now imagine that you also know that the qubit then proceeds to undergo a physical interaction which has the effect of swapping the qubit's x and z value. So at first you knew the z value was +1, but you didn't know the x value. But then you know an interaction occurs which swaps the values. So by logical extension, you now know the x value and not the z value. In this case, you know the x value to be +1. So your expected vector would have to change to 1 + 1, 0, 0, because now you know the x value, but you don't know the z value, because you know the physical interaction swap the two values. Hence, the physical evolution of the system also evolves your knowledge about the system, and thus you can update the expected vector accordingly. So now we're going to talk about expected operators. So every physical interaction can be described by what's called an operator. These operators are like truth tables that describe how your knowledge of a system would evolve as a result of the physical interaction. You have inputs, which are your state of knowledge before the interaction, and you have outputs, which is how your state of knowledge changes after the interaction. So every physical interaction you can describe with one of these operators, and each operator is a matrix. Now, once we've defined both an expected vector and an expected operator, we can apply the operator to the vector just by multiplying the vector by the operator. The resulting vector will be updated to reflect the change in one's knowledge about a system before and after the physical interaction takes place. So there you can see a very simple equation. You just take the vector before the operator is applied, and you multiply it by the operator, and that gives you the vector after the operator has been applied. Now, here are some actual examples of some operators. So the first operator is called the x operator, and it negates the y and z values. Then you have the y operator that negates the x and z values, and you have the z operator that negates the x and y values. The last one here is the h operator, and it negates the y value, but it also will swap the z and x value. Now here's an actual example. So on the bottom right there, you have a little quantum circuit you might see for quantum computing, and you have an H operator followed by the Z operator followed by the H operator. Now remember how we said that we can relate qubits to traditional bits by saying when it's 0, that means z equals +1, and when it's 1, that means z equals -1. Now in every quantum circuit, qubits start with an initial value of 0. So that means they start with an initial value of z equals +1. So our expected vector would begin as 1, 0, 0, 1. Now the first thing we do is apply the H operator, and that's going to swap the x and z values. So that means the 1 that's in the z place will swap with the 0 in the x place. Then the next step, we apply the z operator, which will negate x and y. So beforehand we knew x equals +1. Since this operator has negated it, we know that x equals -1. And the final step, we apply the H operator again, which is going to swap the z and x values a second time. Beforehand we knew x equals -1, but now we know z equals -1. So you can say for certainty that at the end of this program, the qubit will have a z value of -1. Or we can say that the qubit's value is just 1 if we're comparing it to a bit, which is either 0 or 1. So now let's talk about multipartite vectors. So that might sound like a scary word, but multipartite just means multiple parties. So you're talking about vectors of more than one qubit. We can represent systems of multiple qubits simultaneously by taking expected vectors for singular qubits and combining them into a vector for multiple qubits with the Kronecker product. So I'll probably link in the description a video on the Kronecker product in case you don't know what that is, but it's a very simple mathematical operation. So for 2 qubits, if we take the expected vector of the most significant qubit and the least significant qubit, and we compute the Kronecker product of those two vectors, we get a combined expected vector for both the most significant and least significant qubit. And this expected vector will have the form as you see at the bottom here, with this big vector. Now, I is always equal to +1, so the first element is again 1. If you notice, the next 3 elements are ix, iy, and iz. And if you multiply anything by 1, it doesn't do anything. So those are just equal to x, y, and z, but those are very specifically the x, y, and z of the least significant qubit. There are other places in the vector where we have xi, yi, and zi. So those would be equal to the x, y, and z values for the most significant qubit. Now the rest of the values represent correlations. So if you look at the second to the last element, zy, we might know that the product of the z observable on the most significant qubit and the y observable on the least significant qubit is equal to +1 or -1, but we might not know the z value on the most significant qubit and the y value of the least significant qubit taken separately. So it's possible to have knowledge of products, but not the individual values. And we'll see why later. We'll show how this can happen. So now let's talk about multipartite operators. So if you have an expected vector for a bipartite system, meaning that you have 2 qubits, the vector will be of size 16. You can also think of a vector like a matrix, where the number of rows is 1, the number of columns is the size of the vector. So this is specifically what is called a row vector. Now let's say you also have a unipartite operator, meaning an operator that applies to a single qubit that we've seen so far, like the x, y, z, and h operator. And those are matrices of size 4 by 4. And you can't multiply a 1 by 16 matrix by a 4 by 4 matrix. We can solve this problem by using the Kronecker product to combine smaller operators into bigger operators, as shown below. So if we take an operator that applies to a most significant qubit and Kronecker product that with an operator that applies to a least significant qubit, we get a single bigger operator that applies a specific operation to the most significant qubit and a specific operation to the least significant qubit. As an example, let's say we want to apply the h operator to the most significant qubit, but we don't want to do anything to the least significant qubit. We can just take the h operator and the identity matrix, which is an operator that does nothing, and we can Kronecker product them together, and then we'll get a 16 by 16 operator. Then we can actually multiply that by our 16 vector, and the result of that will apply the h operator to the most significant qubit while doing nothing to the least significant qubit. Now let's talk about this very important topic of measurement, because there's a lot of confusion around the concept of measurement. So let's say we want to represent the simplest possible measuring device. A measuring device will need 3 things. First, you'll need at least 1 qubit to represent the measuring device's memory state. So this represents what it actually records when it makes a measurement. Then we need to specify a pointer. So remember that we have 3 observables, x, y, and z. When the measurement device makes a record of something, it will record that onto one of its observables. And the one that's doing the recording we can call the pointer. So the third thing we need is an operator, because a measurement is a kind of physical interaction. And an operator describes physical interactions. So we need an operator that will describe an interaction between 2 qubits that has the result of copying a particular observable of the qubit we're measuring onto the memory state of the qubit for the measuring device. So if we have these 3 things, then we could define a very simple measuring device. So let's talk about an idealized measuring device. What if we had the perfect possible measuring device that we can think of in our head? For an idealized measuring device, you can look at this table at the bottom. We have the inputs and outputs after we apply a bipartite operator. We have our 2 qubits labeled as memory for the measuring device, and the qubit that we're actually measuring. Now, if you can see, the only thing that happens on the output is that the z observable of the memory state of the measurement device, which again is our pointer changes to the value of a zq, which is the value of the observable of the qubit we're measuring. Nothing else changes. Nothing else is perturbed. This is a perfect measuring device. However, this measurement device is not physically realizable because all operators must be time reversible. This is just a physical requirement in quantum computing that any operator must be reversible in time. That just means that if you take the operator and you multiply it by its own time reverse, then it should cancel itself out. And so you see that on the bottom right. The time reverse of an operator is just that operator transposed. So if we take the operator and we multiply it by the transposed variant, then we get the identity matrix. And as we said before, the identity matrix is like an operator that does absolutely nothing. So if you take a system and you apply an operator to it, and you apply the time reverse, it should go back to its initial state. So it just cancels itself out as if you did nothing. Now, why isn't this idealized measuring device physically realizable? Well, because there's not enough information on the output to derive the input. Because if you notice that the value of Zm, which is the pointer, is simply being overwritten by Zq. So the information about the original Zm is destroyed. There's no way you can look at the output and derive what the original Zm value was. So we can't actually define an operator that describes such an idealized measuring device. So now let's look at a semi-idealized measuring device. We can make the operator time reversible by setting the output to be the product of the observable it is measuring, as well as its own observable. So as you can see in our table, the output is now ZM times ZQ for the value of the pointer of the measuring device. This is time reversible because we can just divide the pointer's value by the qubit's value and recover the original pointer's value. This requires us to know that the initial value of the pointer is +1. Because if we know for certainty that the original value of the pointer is +1, then ZQ is the same as ZM times ZQ. Meaning that the value of the pointer will reflect whatever the value of ZQ is, and therefore the pointer will reflect the value of the qubit it is measuring. However, this actually still violates another rule, which is that an operator has to be completely positive. You can actually take each expected value and break it apart into probabilities for the positive or negative measurement result. So recall that I said that an expectation value is just a weighted probability of getting +1 or -1. Well, you can break those apart into two probabilities, the probability for +1 and the probability for -1. And naturally, all probabilities should range from 0% to 100%. An operator that isn't completely positive can produce invalid probabilities, such as negative probabilities. So on the bottom right there's a simple test if it's completely positive, where P is the operator version of each observable, so that's our X, Y, and Z, and O is the operator you're testing. You sum all that, check the diagonals. Are they all positive or 0? What you're effectively doing is checking the effect of each operator on each observable and just verifying that they're all positive. And so this semi-idealized measuring device actually isn't even physically realizable either because it's not completely positive.